Okay, so today we are going to see the formula by Feynman and Kac. Okay, and we are also going to see the proof of the formula. So this is a theorem. This is saying that given a backward heat equation, so here that heat equation appears that V is a function of time and space x. So we assume x is a member of d-dimensional Euclidean space. Here v del t appears. So, partial derivative of v with respect to time, and then the Laplacian of v multiplied with half Laplacian v plus g, this is another function, okay, is equal to k times v. So, the unknown v appears here, here and here. So, it appears first order term with time derivative, second order space derivative, and a zeroth order term. And this equation, we would like to solve this equation with a terminal condition capital T at time capital T. This v capital T is f function f, okay, where this function g, k, f all are continuous. So, here more better description is given. So, here we assume f, which is the terminal condition, is a continuous function which is taking point x to real number. So, R d to R. The function k, which we call potential function, k is also function of x. I have not written the dependency of k on x, as I have not written dependency of v with respect to time and x, but these are understood. So, k is also a function from R d to real number, but here non-negative real number 0 or positive. Okay. So, that is the assumption on k, and k is also continuous. Again, this g function, this is also a function of time and space. So, g is also a continuous function. So, here this time variable is restricted to 0 to capital T, the compact set. Okay. Good. So, this is the theorem. Okay. This theorem is saying that let v be a function C12, that means once differentiable with respect to time, and this v function, okay, the solution v, okay, we are going to look at this. So, v is once differentiable with respect to time and twice differentiable with respect to space, okay, and solves the equation 1. And here the growth property, that v satisfies this growth property, and also g. So, mod of v and mod of g supreme over all possible time, okay. So, that is less than or equals to k times this capital K is different from this small k, okay. So, this capital K times e to the power a norm x square, okay. And here this a is positive number, which is 1 over 2 times capital T d. Remember, what is my capital T? Capital T is this terminal time, and d is the dimension, okay. So, this a is like that. So, we have some upper bound of a, okay, a should be less than 1 over 2 t d, okay. That means, you know, that if capital T or d is large, then a upper bound is smaller. So, with that a, this, you know, norm of mod of v and mod of g, this addition should be less than or equals to this this number, okay. So, that is the assumption on the solution space, okay. So, this is the solution space we are looking at, and we are looking at that this theorem says that if that is the case, then the solution v can be written as conditional expectation of some function of Brownian motion, okay. What is this? So, let us read this. Then v of t comma x. So, now here I am writing down the explicit dependence on v on t and x, that is conditional expectation of small f, which is the terminal condition, of w capital T minus small t into e to the power of minus 0 to capital T minus t k of w s ds. So, this small k is the potential function, but this capital K is just another, this is not same as small k, correct. This is another constant, okay, some positive constant. So, small k of w s ds plus integration 0 to capital T minus t g of t plus theta w theta, and this function is the function of theta, and that is multiplied with this exponential function e to the power minus 0 to theta k w s ds, and then this product is integrated from 0 to capital T minus t with respect to the value theta, with this variable theta, and this conditional expectation we are finding out given W0 is equal to x. That means Brownian motion is starting from x. Okay. So, this thing we can also rewrite. It is easy to do that by some change of variable. So, here that instead of 0 x, I can think that Wt is equal to x. Okay. So, since Brownian motion is time homogeneous Markov process, we can do that. So, I add t value to every time wherever it is. So, then this becomes given Wt is equal to x, and capital Wt minus t becomes capital Wt, capital T. Okay. So, here I do not have minus t, and here small 0 to capital T minus t becomes small t to capital T. Okay. And then this g also becomes g theta W theta when theta runs from small t to capital T. So, here theta was running from 0 to capital T minus t, but t plus theta, if we denote this whole thing as theta, then that is running from small t to capital T. So, these are the adjustment one can do, and one can get another alternative expression. What is the benefit of this expression? That okay, I mean this is precisely saying that f is evaluated at terminal time of W, okay, and f is the terminal data. Okay. So, it is in that sense more intuitive. Okay. And here this is like capital T to small t, that you just when you want to find out V at time small t, which is little past than capital T, then you just need to look at the interval small t to capital T. Why? Because the data is given for capital T, and now it is inside, okay, little past than capital T. So, you need to integrate small k from small t to capital T, etc. So, all this integration is from small t to capital T. So, this expression is a little more intuitive than the earlier one. Okay. So, what is the conclusion from this statement? The conclusion is that the solution is unique, because when I say that okay, this V if satisfies equation 1 and satisfies this growth condition, then it has this expression. It intrinsically says that okay, this should be unique. There is no other thing, okay, because this right hand side expression is uniquely given. Okay. So, now we can compare this result with Tikhonov's uniqueness criteria for a special case. So, in that special case G was 0, K was 0, and there we just had this thing that V was less than or equals to K times 8 into norm x square. Okay. So, this is consistent with that idea. Okay. So, a sufficient condition for existence of a classical solution to 1. Okay. So, this is because earlier theorem does not say that when does it exist, it just says uniqueness. Okay. If it exists, it is unique, but now one can ask very naturally that what is the sufficient condition for existence of solution to that equation. So, this is one set of conditions, that small k is bounded and uniformly Hilbert continuous on compacts on R d, and G is continuous on this domain and Hilbert continuous in x uniformly with respect to t and x. Okay. And small f. So, basically we need to put conditions on all these given data k, g, f. Okay. So, for f we assume that it is continuous and has at most polynomial growth, that is for some capital L and gamma. You can write down that okay, mod f is less than or equal to capital L times 1 plus norm x to the gamma. So, like polynomial kind of thing. Okay. So, we start proof here. In the theorem, we did not assert existence of solution, but rather we asserted that if solution exists, then how should that look like. Okay. And we have stated an expression, and that dictates that the solution, if exists, should be unique. Okay. So, in this proof, therefore, we start with that assumption that solution exists, and then we derive. So, here V is the solution. So, here assume that V is the solution of the equation. So, here we write down V of t plus theta comma W theta, and we multiply with e to the power of minus 0 to theta k W s ds. So this thing as a function of theta, okay, you think that theta is like a time-like variable and you are writing differential of that. So we are considering the whole thing as a stochastic process with parameter theta, okay, and then we are applying Ito's formula on this, okay. And then here, since we have product, so for applying Ito's formula, we need to first say apply on say Ito, the exponential term, and then v terms would remain. So if I do that, so the derivative of exponential term would give me minus kws, okay, and then we are going to get something like minus kw, but here say we are going to get theta, okay, minus kw theta, and then we are going to get the exactly this term v term and e to the power of this term, okay, from this side. And then if we differentiate the v, okay, on v, and e we keep unchanged, so there we are going to get exponential this term as it is, and for v dvt, okay. So there we can use the Ito's formula. So that Ito's formula looks like, say, there would be one del v del t term, correct, and there would be the half Laplacian term for this, okay, half Laplacian of v term, and that would be multiplied with d theta, and then there would be the first order derivative with respect to the space variable, and that would be multiplied with the dw theta. So this is the more local martingale term. So here del v, the gradient of v actually, okay. So the gradient of v dw theta. So that would be the kind of terms. Now at this stage we are going to use that the fact that v solves the PD. Till now I have not used, I have just used the fact that v is smooth, because since v is the classical solution of the PD, so v is continuously differentiable with respect to time and twice continuously differentiable with respect to space variable, etc. So we have just used that, okay. So now we are going to use that, okay, v is indeed the solution. So in the solution we already know that del v del t and then these things and minus k, etc. we are going to get d from there, okay. So let us quickly look at the PD. So here we see that del v del t plus half Laplacian v in the first page, Laplacian v, that is half Laplacian v is equal to kv minus g. If you have minus kv here, so g goes on the right hand side, so minus g. Okay, so we understand that when we apply Ito's formula in this product, we would get minus g of t plus theta w theta d theta term, okay. And of course the term with integrated with this to Brownian motion, this local martingale term, this would remain, okay. So this term is here, okay. So this is dot product, correct, this dot product. So you are going to get a summation I is equal to 1 to d del del xi v of t plus theta w theta d w theta, okay, ith component of that, okay. So that is the expression for this part. And now what are we going to do is that we first integrate, because we have to get rid of this differential term, and after integrating from 0 to r minimum Sn, which I am going to define what is r and what is Sn, then we are going to take expectation, okay. So here we mention what is the range of theta on which I am integrating. So theta would be integrated from 0 to r minimum Sn, where r is a member between 0 and capital T minus small t, okay. So that t plus theta becomes a member between small t and capital T, correct. Theta between 0 to capital T minus small t implies small t plus theta is in between small t and capital T, okay. So that is my R, and Sn is a stopping time introduced to localize so that the Brownian motion remains bounded till time Sn. Okay, so here infimum over all possible t such that the norm of Brownian motion, okay, is greater than n times square root of d. What does it mean? It means that the hitting time of Brownian motion, okay, or exit time of the Brownian motion from the ball of radius n times square root of d. So this Sn is the exit time. Next, we get v of t comma x is equal to expectation of v of t plus r minimum Sn comma w r minimum Sn into e to the power of integration minus 0 to r minimum Sn k w s ds given w0 is equal to x plus this another expectation. So how are we getting these three terms? We are getting directly from integration, because left hand term is going to give me two terms, because the left hand side after integrating we are going to get v of t plus r minimum Sn, and then instead of theta you are going to write down r minimum Sn. Okay, so that would be one term, and then subtracted minus v of, so here we are going to get minus v of t comma w0 e to the power minus 0 to 0. So this integration 0 to 0 is going to give you 0, so e to the power 0 is 1. So I would get v of t plus s minimum rn w s minimum rn times e to the power of this term minus v of t comma w0 only. But we are taking w0 is equal to x, correct? So we are going to take conditional expectation. So on the left hand side we are going to get v of minus v of t comma x, that term. Okay, and from the right hand side here this local martingale term, that where Brownian motion is there, this term after taking expectation it will be 0. I mean, here what is happening that since I am integrating only till time Sn, there the Brownian motion is bounded. So the v of t plus theta w theta, okay, so that function would be bounded function because the variable w theta is bounded by a ball. So v function which is continuous function, that is now restricted on a compact set, so it is a bounded function. So it is integration of a bounded function with this Brownian motion till a stopping time. So we are going to get a martingale term, okay, and that would have expectation 0. So from the right hand side only one term would survive. Okay, so two terms on the left and one term on the right. So you are going to get three terms. Okay, so here we got three different terms. One is so two terms coming from left hand side, and this part would become after integration and then taking expectation, this part would become 0. So from here the one term would be v of t plus r minimum Sn w of r minimum Sn times e to the power of, here also for theta you write down r minimum Sn, and then subtracted with v of t plus, instead of theta you are writing it 0, that means t or just vt comma x. Why? Because w0 is equal to x. Yeah. Okay, so then rearranging of term would give you v of tx is equal to expectation of v of t plus r minimum Sn w r minimum Sn e to the power of minus 0 to r minimum Sn k w s ds given w0 is equal to x plus expectation of integration 0 to r minimum Sn g of t plus theta w theta e to the power of minus 0 to theta k w s ds integration of this to theta given w0 is equal to x. Okay, this 0 is coming from the expectation of 0 mean martingale. Okay, next what we use the growth property that g is less than or equal to k times e to the power a norm x square, and here if we replace x by the Brownian motion w theta, then that random variable has finite expectation. So using this, okay, we can actually, that means that dominate g of t comma w theta by one random variable with finite expectation, okay, because here right hand side, okay, is this k times e to the a w theta whole square, that does not depend on time t. Okay, so this would be used for applying the Dominator convergence theorem. So here we use that, we take so this expectation of integration 0 to r minimum Sn gt plus theta, this expression was there earlier also. Now we take n tends to infinity and r approaches to capital T minus small t. So when you do that, we can take this limit inside of the expectation using this Dominator convergence theorem, and then when we take it inside, we get 0 to capital T minus small t. Okay, so this r minimum Sn converges to capital T minus small t. Why is it so? Because as n tends to infinity, Sn goes to infinity almost surely. Why? Because Sn is nothing but the time to hit a ball of radius n times square root of d. As n goes to infinity, the ball becomes larger and larger, so Sn becomes also larger and larger with probability 1. And on the other hand, r I am also increasing to capital T minus small t, so I would get here capital T minus small t here. Okay, so g of t plus theta, and the integrand is g of t plus theta w theta e to the power of minus 0 to theta kw s ds, and then everything is integrated with respect to theta. So here this whole thing can also be rewritten as expectation of integration small t to capital T g of theta w theta, and this term. Here, why can we do that? We can do that because that we are just shifting time from 0 to t. Okay, whatever is on the right hand side, you see that condition was given in the earlier line was w0 is equal to x. Now if I declare that as per time t, okay, so wt is equal to x, then every time every other time point would be changed, okay, that would be just shifted to small t unit away. So then 0 becomes small t, capital T minus small t becomes capital T. Okay, so therefore, so in this last line, you got integration, this lower limit is small t and upper limit is capital T. And then in the integrand, what you have g of t plus theta, where theta was running from 0 to this, then you can write down, you know, by change of variable, that is g of theta itself, where theta is changing from small t to capital T. Okay, okay, so let us see. So here, so Brownian motion I have changed. So Brownian motion w, I mean this w theta, I mean that would change to, I mean earlier whatever w theta was there, now it should be t plus theta. Okay, but here also, since we have changed t plus theta as theta, so I can keep the same notation w theta. Okay, there is two change of, you know, notations. Okay, so g of w theta, and then in the e to the power form, so earlier the w was from 0 to theta. Okay, now since we have changed the time of the Brownian motion, so w s ds s should run from t to t plus theta. So here first we have changed the time index of Brownian motion. So here w0 to wt, so then this thing should have become t plus theta, wt plus theta, and here this 0 would become, so if this is t, then this integration e to the power minus t to t plus theta should appear here, and then in this we do further another substitution, that we change t plus theta as theta, so this becomes g theta, and wt plus theta becomes w theta, and here since t plus theta is theta, so we write down theta here, and here lower limit of integration becomes, instead of 0 we get small t, and upper limit instead of capital T minus t we get capital T. Okay, so after obtaining this expression, we now next mimic the procedure for proof of Tikhonov's theorem. Okay, we use the technique of Tikhonov's theorem. So what we do is that we write down this event, okay, into this this inside integrand as sum of two different terms. One term that we get by multiplying with indicator function Sn less than or equals to r. Another thing we obtain by multiplying indicator function of Sn greater than r. So indicator function of these two mutually exclusive and exhaustive events, if you add, you get 1, correct? So 1 can be written as sum of indicator function of these two mutually exclusive and exhaustive events. So that we do in the next slide. We consider only first the case when Sn is less than or equals to r. We have done exactly the same thing in the proof of Tikhonov's theorem also. When we do this, our expressions become simplified. So why is it so? Because earlier we had integration 0 to r minimum Sn. Okay. Now if Sn is less than or equals to r, so r minimum Sn is Sn itself. So here look at equation number 5. In the 5 you have r minimum Sn, and then so that thing we are writing down as v of t plus Sn comma Wsn into e to the power of minus integration 0 to Sn k Ws ds, indicator Sn less than or equals to r given W0 is equal to x. So this is dominated by, so now we are going to get some domination of these, but before that let us clarify that what are the other terms I am not writing here. So in this bullet 5 we are writing this term v of t plus r minimum Sn, so this term here, okay, and we are not writing the other term, the g term, okay, integration g term, that we are not writing here. We are just writing the v of t plus r is in that term, okay. So for that term we are now getting one estimate, upper bound. For upper bound, what are the things we are doing? We are replacing this e to the power of minus of this term by 1, okay, because k is non-negative. So this e to the power of minus 0 to Sn k Ws ds is less than or equals to 1. So it is dominated by this term, that when this exponential is replaced by 1, and then indicator function of Sn less than or equals to r is smaller than indicator function Sn less than or equals to capital T minus small t. Why is it so? Because r is smaller than capital T minus small t. So Sn less than or equals to capital T minus small t is a larger event. So indicator function of this is a larger function. So I mean not strictly larger, but okay, I mean not smaller than this, okay. So we are going to get this estimate. Now here we use the growth property of v. Growth property of v is saying that v of t plus Sn Wsn is less than or equal to k times e to the power of norm of mod x square, but x is here the Wsn, and Wsn is what? The position of the Brownian motion at time Sn. At Sn, Brownian motion lies on the surface of the ball, okay, on the sphere of radius n times square root of d. So the square of that would be n square into d. So ek times e to the power ad n square appears here to estimate that v function. Now what remains is the indicator function. Expectation of the indicator function is the probability of the event. So we write down that is probability Sn less than or equals to capital T. Here again further we have removed small t, capital T minus small t I have removed to get even a larger probability perhaps, okay, because capital T is greater than or equals to capital T minus small t. So here this estimate is independent of small t. Okay, so we could dominate this expectation by some quantity which is independent of small t. This we can again further get a better estimate. Here Sn less than or equals to capital T, that means that Brownian motion touches the boundary of the ball before capital time T. That means that if we look at the components of Brownian motion, so the Brownian motion's modulus is more than or equal to n times square root of d. So that means its square of the norm is more than n squared times d. Okay, and then that square of the norm, so the norm of x square involves summation xi square I is equal to 1 to d. So there are d number of sums. If the whole sum is greater or equals to n squared times d, greater or equals to n squared times d, that means at least one of the term must be more than n squared. Right? Sum of d number of positive terms is more than n squared times d. So at least one should be more than n squared. So that means at least one of the component xi should be more than n. Okay. So at least one of these components of the Brownian motion is more than n. And then that probability would be upper bounded by sum of the probabilities of the terms should be more than or equals to n. So here we get, because at least it's like union, correct? So probability of union of events is less than or equals to sum of the probabilities. So we are using that. So sum of j is equal to 1 to d, probability of this maximum of Brownian motion in between 0 to capital T, that is more than or equals to n. So this is the justification. Okay, so now we get that right hand side is less than or equal to, so here what we use reflection principle. Right hand side is less than or equal to 2 times, so here I did not have 2, I had just k times e to the a d n square earlier, but now I am getting 2. Why? Because I am replacing maximum 0 to capital T by capital T itself. Okay, the probability that w capital T, okay, at the component j is greater or equals to n, okay, plus probability minus wt greater or equals to n, okay, given w0 is equal to x. Okay, so this is coming from reflection principle, what we have already seen in earlier class. So now here from this we consider n tends to infinity. When we take n tends to infinity, I mean, we would like to see that whether this whole thing goes to 0 or not. Here we see e to the power a d n square. As n tends to infinity, this term grows in large. However, the other terms where Brownian motion is greater than or equals to n, that terms goes to 0. And then what would survive? So we see that that probability that wt greater or equals to n, that probability is less than or equals to square root of t by 2 pi 1 over n, so minus or plus depends on plus or minus, here we are talking about e to the power of minus n square by 2t, n minus plus xj whole square by 2t. Okay, so this xj is the jth component of initial position x. So that does not, the value of xj does not matter much, as we are talking about large n. So what matters is actually this denominator 2t. Okay, so here if we choose a is less than 1 over 2td, okay, so then this adn square, the way it becomes larger, okay, would be dominated by the way the e to the power of minus n square by 2t goes to 0. Correct? As n tends to infinity, this whole term e to the power exponential term goes to 0. Correct? So this convergence to 0, this would dominate this growth if a is smaller, the coefficient ad is smaller than 1 over 2t. Okay, so that is the idea. And since we have assumed that a is less than 1 over 2td, so this is true, and we can get this, above, this upper bound goes to 0 as n tends to infinity. So what does it mean? It means that the expression in the bullet 7, this expectation that goes to 0 as n tends to infinity. Okay, so expectation of v of t plus r wr e to the power of minus 0 to r kws ds 1 Sn greater than r. So here I am considering the other part of the event Sn greater than r. Okay, so you remember that we promised that we are going to have two different terms. Only we talked about one term there when Sn is less than or equals to r. We are considering Sn greater than r. So in that case, r minimum Sn becomes r itself. So we are getting v of t plus r here, wr here, and e to the minus 0 to r here. Okay, and then here this thing again we are going to consider the limit. Okay, so as n tends to infinity and r tends to capital T minus small t, then v of t plus r would become capital T. Okay, and e to the power of minus 0 to r, that means e to the minus 0 to capital T minus small t, and here Sn. So as n tends to infinity, what happens that Sn goes to infinity with probability 1. So r is on the other hand a small number between capital T minus small t. So the probability that Sn would be more than r grows to 1. Okay, so this indicator function grows to 1 with probability 1. So I am going to get only 1 here or nothing. We do not need to write down this again. Okay, so here this limit is easily obtained as n tends to infinity. What happens? So using Dominator convergence theorem, we can put the limit inside because all these things are bounded here. Okay, so now we use Dominator convergence theorem not because v is bounded, because here not because of that, but we can use it because v has that growth property for which we can take the limit inside. Okay, which we have already discussed earlier. Okay, so now this whole thing, we know that v is the solution of the PDE. So at time capital T, v satisfies the terminal condition. The terminal data is small f. So v of capital T of wt minus small t is nothing but f of w capital T minus small t. Correct? So this is same as small f of w of capital T minus small t. And then what we do is that we change variable. Okay, we do say change of variable here. So we just shift the time of Brownian motion from 0 to t. So earlier it was w0 is equal to x. So I'm writing wt is equal to x. So we are assuming that is starting from time t. Then everywhere, wherever your capital T minus small t was there, it would be capital T itself. And the integration minus 0 to capital T minus t is becoming now integration minus small t to capital T. Okay, so we get this expression now. Okay, hence by taking limits in the bullet 5. Okay, so what is bullet 5? This one. Okay, this whole thing that I have written as, the first term was written as sum of two different terms. One term, okay, that goes to 0 that we have proved, and another term is going to another limit. Okay, and then this g term remains there. So when we take that, then we get that the formula here, that v of t plus x. So we go to the slide number 2 here, that in the statement of the theorem, v of t comma x is equal to expectation of this thing, f of wt e to the minus small t to capital T kws ds, that we have just obtained now, and that integration g things, that is as it is here. Okay, integration g theta w theta, this thing. So here bullet number 5, we had r minimum Sn, only, but as n tends to infinity, this Sn would also go to infinity, and we do take r tends to capital T minus small t. So the expectation of integration of g function would converge to the term which is appearing in the statement of the theorem, that integration small t to capital T g of theta w theta e to the power minus this thing. Okay, so actually, here the statement is written with two different versions, where conditional expectation was given w0 is equal to x, another was wt is equal to x. So both the versions were written here. Okay, so as a corollary of the earlier earlier this theorem, what we have proved now, we can write down that look at the equation del u del t plus kt x u is equal to half Laplacian u plus gtx. Okay, u0 comma x is equal to fx. Okay, so here it is the initial value problem. Earlier we talked about terminal value problem. Now if you consider an initial value problem, what happens? That Laplacian is on the other side of the equality. Okay, terminal value problem, that del u del t and Laplacian was on the same side of the equality, but here it is on the other side of the equality. That you get just by changing the variable t minus small t as t. Okay, so then get the negative sign, etc., and it would appear. So for this, we can, since this, the terminal value problem and initial value problem can be related or can be connected with only this small change of variable. So the same result applies there, only suitable change of variable there. So we write down here. So for every capital T greater than 0, there exists one k positive and one a less than 1 over 2 t d, such that if that mod of u plus maximum supremum norm of g is less than or equals to this growth condition k times e to the power of a norm x square, then as a goes to 0, as t tends to infinity, then u of t comma x is written as expectation of f of wt e to the power of minus 0 to t kw is ds, and integration 0 to t g of t plus minus theta w theta. See, earlier we had d plus theta, but here we are going to get t minus theta w theta e to the power minus 0 to theta kw is ds. Given w0 is equal to x. So earlier our integrand in the expectation, the random variable, was like of the form f of w capital T minus small t, correct? So small t, that running variable, always has a negative sign there. Now here it is not, it is just, since the time change happened, so f of wt is appearing here. So that is the result. So we stop here. Thank you.